And yeah, what I've just called various phenomena of Bayesian analysis. And what I mean by this is this effect that Bayes' theorem effectively encodes what's called Occam's razor. Or you could say that Occam's razor sort of predates the logic of Bayes' theorem, depending on your point of view. We looked at, let's say, consequences of marginalization. And I want to spend 5 more minutes on this now afterwards. And something we didn't consider, but I'll list it here, as we'll discuss it now, is that Bayesian reasoning effectively penalizes what we can call fine-tuning. And we'll see a concrete example of this. So, say I have this example here. Right, so we looked at, for instance, this example, which was a Bayesian analysis of where the end result is a 4-dimensional posterior, and how this can be presented or visualized in this way as all the possible 2-dimensional marginals and 1-dimensional marginals. And then we discussed how what can, or the question is what can cause the posterior to become high for some parameter region. And we know that the posterior is okay, it's likely times prior, but then if it depends on some extra parameter, you integrate over that parameter. So it's a sum or an integral over likelihood times prior. And that can give you a large contribution in sort of 2 different ways, right? Either you can have, you might integrate a small region with a fairly high likelihood times prior product, or you can integrate a large region with a not so high likelihood, but it's compensated by the fact that you're summing over a large region. So this is one of the things that we need to be aware of. So I'll just draw a quick illustration of that. So keep in mind, let's say 2 ways for marginalization to give a large posterior. So let's try to make a drawing of this. So say I have a 2-dimensional posterior, 2 parameters, theta 2, theta 1, and say that so I'm viewing my posterior distribution from above, and say it looks something like this, where it's peaked in this region, something like that. Then it falls off outwards here. Not the best drawing that you see, but I think you get the idea. Oops. Stop sharing now. Separate. Right, so this drawing is supposed to now represent the joint posterior of theta 1, theta 2. So that's the posterior, so it's given some new data. But now if you marginalize or integrate out parameter 2, then I'm just going to draw this upside down here, then your marginal distribution for theta 1 might look something like this. This is now your marginal distribution for just theta 1. And the point is just that, okay, if all you knew was that 1D marginal, you see it has 2 peaks, and you don't intrinsically know whether it comes from the right-hand case where you're just integrating a low posterior over a large volume, or the left-hand case where you're integrating a high posterior over a small volume. So this is one of the things that we need to keep in mind when interpreting marginalized posteriors. The other thing I wanted to discuss was that Bayesian posteriors penalize fine-tuning. And it's effectively related to this question here, but it's just that, okay, if your likelihood, so if your some high dimensional likelihood is high along some, let's just call it narrow, and I'll try to be more specific, along some narrow region in your parameter space, will make a small impact on the posterior. And now you might ask, well, what is it that defines whether a parameter region is narrow? And it's effectively a choice you make when you assign your prior probability. Because what's regarded as sort of a large and small parameter region, that's, in a sense, that's what your prior probability distribution does, is sort of weighting your parameter space. So imagine you had 2 parameters and you said, my joint prior probability over this 2D parameter space is a flat distribution. It's just a box over my 2D space. If you distribute your 100% prior belief in that way, then say the diagonal theta 1 equals theta 2, then that strip will constitute, or a small band around that strip will constitute a very small fraction of your prior probability. So in that case, that will be a narrow region. A priori, you didn't assign much probability to that region of parameter space. If, however, you decided that actually my joint prior distribution is just a band along theta 1 equals theta 2 and falls off outwards in parameter space, then it's not a fine-tuning region. Right? Then it's actually a big part of your prior belief. But the point here is that very often we don't assign priors like that, right? Very often we do assign our priors sort of spread out across a large parameter space. And then if, say if you have 2 regions that can, 2 separate regions in parameter space that can give more or less similar good fits to the data. One is some broad regional parameter space over here, and one is along the strip theta 1 equals theta 2. then that broad region will get a higher posterior than that thin region. And I'll show you a specific example. So this is again, it's not actually important what the axes here mean, but what you're seeing here is it's a result of a 15-dimensional parameter exploration, and where these two parameters you see here. So this is actually a dark matter study. So the x-axis is the mass of a hypothetical dark matter particle, and the y-axis is a coupling strength. So effectively, how probable is it that this dark matter particle interacts with the Higgs boson? And in this model that we studied here, we had these two main parameters. These are what we would say are parameters of interest. And then we had, I think it was 13 nuisance parameters, parameters that are not of physical interest or scientific interest in itself, but it's parameters that describe uncertainties in various models, experiments, and stuff like that. So parameters, we need to vary them to take into account all these uncertainties. And what you're seeing here is not the posterior distribution. What you're seeing here is what I briefly discussed, I think at the end of last time, what I call the profile likelihood function. So this is just a plot of the likelihood function, but of course the likelihood function itself is 15-dimensional. And there is no sort of, as far as I know, there is no sort of principled way if you're just focusing on the likelihood function, which is not a PDF, right? So it's not a natural thing to integrate it, or that's not necessarily a more correct thing to do. So how do you get rid of your 13 extra parameters so that you can visualize a 2D space like this? Well, one option would be to fix them to chosen values, right? But then your result would only be one specific 2D slice of a 15-dimensional space. And for every new choice of those 13 parameters, you get different results here. But with this profile likelihood approach, you say, for every point in this plane of parameters of interest, I will try to find the values of the 13 other parameters that give me the largest possible likelihood. So it's just showing, at every point, it's showing the maximum likelihood that we were able to find. Of course, we were not able to sort of grid scan this space and for every point actually run a maximization in 13-dimensional space. That would be computationally super expensive. What this rather is that we have tried to sample this 15-dimensional space as well as possible, and then focusing with an adaptive sampler, in this case nested sampling, which will then sample, draw most of the samples in the high likelihood region. And then what you do then is just, for every point in this space, you effectively, you bin this space, right? So for every, say, little square in this space, you look at, of all, say, some millions of parameter samples, of all these parameter samples, which samples belong in this little given square of this 2D space. And of those, say, 100 samples or something, you pick the one with the highest likelihood value. And that's the value you visualize in this column, right? So anyway, what this is trying to show is that it's trying to show, think of it as just now effectively the likelihood function, but it's showing the profile likelihood function. And this star is the point of highest likelihood.
So another way to say this is so basically your parameter space you're interested in is not flat anymore, right? Like the surface gets bent according to the...
Yes, this is, what you're seeing here is effectively a projection of some complicated hypersurface in the 15-dimensional space. Yes. But so this is our profile likelihood result, and the contours here are sort of approximate frequentist, 68% and 95% confidence. Yeah, confidence regions. And notice this vertical strip at the top there, right? Where you have this thin strip, and you can sort of see that the result looks a bit patchy there, and what you're seeing there is the effect of the fact that it's difficult to sample a 15-dimensional space. So probably if we had even more samples, that band would look completely continuous, right, in color. But contrast this to this plot, which is a Bayesian posterior. So this is the same analysis, but now a Bayesian analysis, and what you're seeing is the Bayesian posterior. And now you're seeing that that vertical strip is gone. So now what you're seeing now is the 68% and 95% credible regions, and the vertical strip is gone. And the reason for why the vertical strip is gone is that it corresponds to a narrow region in your parameter space, and the Bayesian analysis will penalize that as being, because it was a priori, by assigning your priors, you were saying that such a solution is a priori unlikely, and in this case, the data wasn't strong enough to really pull that out in comparison to this bulk region here. Right? You can also see that if you look at the maximum likelihood, the best fit point is this point down at the very bottom tip of this region. So if you just did a frequentist analysis, you would say, okay, this is my best estimate for these two parameters, is that point. If you instead did a Bayesian analysis, now this okay, I think, I don't actually fully remember, I think the star is the point of maximum posterior density, and the white circle is the expectation value, so it's the mean, right? And you see that in this case, none of these actually correspond to the point of maximum likelihood. And you see that this mean point is pulled towards the middle of this region, as you might expect. So this is just to highlight that when you're working in high dimensions, these differences between a maximum likelihood and the Bayesian analysis can impact your results, and you have to keep this in mind when you interpret it. Yeah, absolutely.
Is this basically a consequence of the way, so you choose your prior to be somewhat smooth or flat, I guess, and then this is kind of reflected in the smoothness of this shape, or is that, so if you choose a more like higher, something with higher curvature as a prior, would you get more curvature here?
So, good question. I mean,
it's not just curvature, right? It's also location.
Yeah.
In the sense that your prior would need to line up with that narrow band that we saw earlier in order to make that more significant in the posterior.
Yeah, I wouldn't think of it primarily as a question of curvature, but it's effectively when you sum over all these extra dimensions, where does the bulk of your prior probability, or what's often just called prior mass, because when we talk about probability densities, we sometimes then refer to that as sort of probability mass divided by parameter volume. So it's effectively where would the majority of your prior mass live, and only a small fraction of that would live in that thin region. And that's it's not necessarily only because it looks thin in this 2D space, right? It might also correspond to, I'm not sure about this, I don't remember, but it might also correspond to, in order to get a good fit along that narrow vertical strip, perhaps some or many of those 30 nuisance parameters had to be pulled far out into their unlikely regions, right? penalized by their Bayesian priors, but you don't see that in this frequentist analysis. So again, this is.
Can you go back 1 second?
To this one?
To the other one? Yes, precisely. Yeah. So which data point would you record in the end now? Because like mass-wise, they are quite similar, right? But like when we look at the coupling strings, there's a difference of like roughly half an order of magnitude, right?
Yeah.
So what value would you believe in more now? The expectation value or the most probable? Like which value would you record in the end? I guess you guys settled for, well, we're going to report both of them.
Yeah, and effectively, right? And we also probably we also displayed a bunch of okay, we probably also did something like this, that we showed a bunch of the 1D posteriors. But yeah, no, it's just very tricky. Personally, if I suspect that the posterior has multiple modes, like we discussed last time, then I'm always a bit wary about just giving the mean expectation value, because that might that point might have a posterior probability of close to 0. Right? But if you give the maximum posterior point, you at least know that okay, it's not completely unlikely. But yeah, if I was to summarize this, I think without giving a plot, I think I'd do something like the 68 and 95% credible regions starting from the point of maximum posterior. Yeah. That would be my preferred way of doing it. But it's tricky, and again, it's one of the reasons why if you can afford it numerically, I think it's very useful to show both the profile likelihood and the Bayesian posterior, even if all you want to do in the end is perform a Bayesian analysis comparing it to the profile likelihood. Does tell you something about which regions have a high posterior because the likelihood is high. So the model predicted a high probability for the data you saw, and which regions have a high probability, mostly because it predicted an okay likelihood, but over a huge parameter space. But it's tricky business. Yes, okay. I think that's what I wanted to discuss in terms of presentation of results. So then we have discussed the philosophy of Bayesian analysis. We have discussed the components of Bayes' theorem, the evidence and the posterior, how you in principle use them for parameter estimation and model comparison, Jeffrey scale, how to deal with many dimensional posteriors. But it's all been a bit sort of in principle. Now, how do we actually do this in practice when faced with a numerical challenging problem? And as mentioned when we introduced parameter estimation, it's very rare that you can actually find an analytical expression for your posterior distribution. It's also rare where you can sort of find a direct numerical, let's say, approximation or proxy to the posterior distribution itself. It's rare that you can get sort of a numerical function where I pass in my theta and out comes P of theta, right? In the end, what you typically end up with is rather obtaining a bunch of theta samples that when you put them in a histogram, the distribution you get should approximate the posterior distribution. So we need to be able to sample parameter samples draw parameter samples according to our posterior distribution. That's the challenge, and then we'll do our inference based on that set of samples. And then traditionally, this has been solved with some of the many, many different versions of Markov chain multi-color sampling. But that's well suited for parameter estimation, but not well suited for model comparison, because you're not also computing the Bayesian evidence. And for that reason, what I want to now discuss is this other alternative, which is nested sampling, which in effect gives you both the evidence and samples from the posterior. And then there might be more, but the implementations of this that I know of in terms of codes, so let's call them common implementations. So there's one code called multinest, and there's another code called polychord. So personally, I've been involved in work with both multinest and polychord, but personally I'm most familiar with the multinest code. And for multinest, there might be something similar for polychord. I should know this actually, but I don't. But for multinest, there is a Python package which I quite like, which is called PyMultinest. So the original method is due to scaling, and I think it dates back to 2004. And it's primarily a method to obtain Bayesian evidence, so what we call sets, and we get posterior samples as, let's call it the byproduct. So one way of viewing this is that if you just write down Bayes' theorem as say likelihood times prior, well, that should be equal to posterior times the evidence. That's just going to be rearranging Bayes' theorem. And what you can think of is as this is effectively your input, and this is what you hope to obtain. That in this sort of analysis, you provide your prior distributions, and you provide the likelihood function where you model what does my, for a given parameter point, what does my model predict for the probability distribution of the data. So that's your likelihood. So you define those, and then this product should then be equal to your posterior distribution times the evidence, but the challenge here is sort of to be able to obtain these two factors separately. Right? So that will be our output. Sort of this method will enable to disentangle these two. And so we want to compute the evidence, which is then the high-dimensional integral of likelihood times prior over some high-dimensional parameter space. And I'll just give this equation a name, psi. But high-dimensional integrals are hard. That's the challenge of this evidence equation, is that it's a tricky many-dimensional equation. So the question Well, the basic idea behind this approach is to try to think of, is there a way we can turn this integral into a one-dimensional integral? That's the idea. And there turns out there is, by a very clever change of variable, effectively. So, can we turn to one thing? Well, so now we introduce a new variable, and this variable is really the key to nested sampling. And it's a variable called prior mass. So in terms of dimensions, it's an amount of prior probability. It's not a probability density, it's an amount of prior probability. And we denote it by psi, and we let it depend on a parameter, lambda. And the way this variable psi is defined is that it's an integral of only the prior over some part of the parameter space. And which part is this? It's the constrained part of the parameter space where your likelihood is larger than some value lambda. So what it's saying is that, okay, I have my parameter space and I have some region of high likelihood or higher than lambda. So you can imagine some contour of your constant likelihood, and you say within that contour, I will integrate the prior. I will check how much prior probability is within that contour. So personally, I find this easier to think about if I have a figure. So for simplicity now, imagine we only had a one-dimensional model, right? And say we had a prior that had some, I don't know, shape like this. So this can be our prior. And say over this same parameter space we have a likelihood function. Let's just make it something approximately Gaussian-like. Not very Gaussian-like, but you get the point. So this is my likelihood. And then I can define a lambda, which is just now a likelihood threshold. So let's say I put my lambda here. What's the region where the likelihood is higher than this lambda? Well, this region within these two lines, right? So then what is my prior mass? It's this area here below the prior. So that area is now my prior mass as a function of lambda. And as I would lower lambda, I would get a larger prior mass. And I should specify one more thing, that the corresponding infinitesimal amount of prior mass, so d psi is a small amount of prior probability, right? And so it's the prior probability density times some small volume of prior probability. And this relation should make you think of transformations of random variables. So if you have, so I'm just gonna write this in margin here. random. All right, well, if you have two random variables that are related, say x and y, and you say you have the PDF of x, px, p of x, and you want to find, well, what is the corresponding PDF of y, if y is some function of x, for instance, then your starting point for doing something like that is to say that, okay, I will have a mapping so that the amount of probability in some small region of x space should then be the same as the amount of probability in the corresponding region of y space. And how we would typically write that is if you say p of x, px, so that's a small amount of probability in x space, should be equal to p of y, dy, the corresponding small amount of probability in y space, and then you can use this relation to find the unknown PDF, p of y, right? In this case, what we have is effectively that this relation here is saying that your prior pi psi of psi times the psi equals pi theta d theta, which is just saying that your prior for, so this is, it's your prior for the prior mass, which is sort of a convoluted concept, but think of just as, okay, the PDF for psi in this case is just one, right? It's just a constant function for psi in 0 to 1. Because psi is an amount of prior probability, right? So it cannot be larger than 1. It cannot be smaller than 0. So what this relation is saying is that by defining your prior mass in this way, you are effectively saying that my prior probability for this parameter psi is just the flat distribution, flat 1D uniform distribution between 0 and 1. And we will use this later. So let's say the two extreme cases are psi of, so what do you get if you put this lambda to 0? What's the prior mass contained within the region of likelihood greater than 0? Exactly, right. So that would be 1. And the prior mass contained within the region that has likelihood higher than the maximum likelihood, well, that's 0. So that's your corner cases or extreme cases. And we'll take 15 minutes there and then continue after the break. So we have introduced this concept of the prior mass, and the idea behind it is turning the high-dimensional evidence integral into a one-dimensional one. Because one-dimensional integrals are easy to do. And the thing to note about this psi, this prior mass, is that it's a one-dimensional function, but it's a decreasing function of lambda, right? As we just discussed. So psi lambda is a one-dimensional decreasing lambda. As you increase the likelihood threshold, you contain less and less prime mass.
Sorry, but the integral that you take is still high dimensional, right?
No, because, well, we will be computing a different integral, a one-dimensional integral that's just a function of this prime mass, but it evaluates, it's the same evidence. Yeah. this means that we can also look at the inverse of this psi lambda function. In other words, what's if I have a prior mass, what's the value of the corresponding likelihood contour, right? That's the inverse. And we denote this, since this is again a likelihood value, we also denote this as L as the likelihood. It's the inverse function. Is L of psi of lambda, which is just equals lambda, which is now, think of it as the value for likelihood contour contains a prior mass. And this means that we can now express the evidence as a one-dimensional integral. Express that as, so it's a one-dimensional integral over prior mass. And we integrate over the entire range of prior mass from 0 to 1. And what we integrate is this likelihood as function of prior mass. So now we have reduced this into a one-dimensional integral. That doesn't mean that our work is done, because we need to find these values. But what this looks like, try to make a drawing of this. So say again, I have a two-dimensional parameter space, and I will draw some contours of constant likelihood just to see a map of the likelihood function. Say I have this is some low value of likelihood, some slightly higher value of likelihood, some slightly higher value of likelihood, and some high value of likelihood. So I'll just call these L1, L2, L3, L4, some fixed likelihood values. And then if I now plot a one-dimensional function of prior mass from 0 to 1, and I now make a plot of this L of psi, then we know that the likelihood value that contains all of the prior mass, that's the likelihood value of 0. We know that the value of likelihood that contains 0 of the prior mass, that will be maximum likelihood value. And then say these 4 contours of likelihood, where L1 is the lowest likelihood value, they will correspond to decreasing values of prior mass. So for instance, we'll have a point maybe here, which will be psi 1, L1. Perhaps we have a point here, which is psi 2, L2. I don't know, point here, psi 3, L3. Point here, psi 4, L4. And for instance, this prior mass within this region, right? Or not the prior mass, the contribution to the evidence from this highest likelihood region, well, that will correspond to, say, if that will correspond to to this part, and similarly in decreasing likelihood contour. So there is some, of course, we now only have 6 samples of it, but there is some proof function here, right? Perhaps does something like that. There is some true function, but we don't know that function at every point. Currently, we only have 4 samples of it. But the point is that if we can, so now the evidence, right, set is just the integral of this one-dimensional function. So set is just this area under here. So the point is that if we can obtain this series of samples, the pairs of samples psi1, L1, psi2, L2, psi3, L3, if we can obtain a sufficiently dense sampling of that one-dimensional function, then we can just compute that integral with trivial 1D integration methods like the trapezoidal rule or whatever, right? But the point is that if we can get, we need a set of ordered pairs of samples psi I, Li. So if we can get this, we can evaluate sets as a one-dim integral, for instance, by so I mean the choice of integration method in that case really doesn't matter. That will not be the dominant uncertainty. But the point is that it's trivial once you have those samples. And what nested sampling is a technique to get this set of ordered samples. Okay, so what I'll do now is that I will just write down the algorithm and I'll show you an illustration of it and then go through the details of why it works. But I think it's useful to just see the algorithm first and then we can worry about why it makes sense, if it makes sense. Nested sampling is a type of sampler, sometimes referred to as a population sampler. And what that means is that you're constantly working with a fixed population of parameter points. So it's not like a Markov chain where you're walking on a chain and just sampling one new point at a time. You have a population of points, and that population of points evolves in some way. It's not a differential evolution or genetic algorithm, but it's still you have a set of points that move around in parameter space. And in nested sampling, these points are referred to as live points. So you draw and you decide on some number, n. So this is one of the parameters of this algorithm that you need to decide on. So you draw n live points. And you draw these according to your chosen prior, according to your officially you draw them according to your joint prior over this many dimensional parameter space, but very often in practice your joint prior is just a product of one-dimensional priors. So you draw a set of live points, you evaluate likelihood at each point, at each line point. And now, sort of the two key steps is that first you discard, but record, so you need to keep track of these. Points with lowest likelihood. Just find the point of these n samples with the lowest likelihood, and you say, okay, I'm going to record that parameter point, but discard it. It's now killed. It's no longer part of my population of points. So now I'm 1 point down. And then the key step is that, okay, you sample a new point. So draw a new point, and you sample it again from the prior, but you impose an additional constraint with additional constraint, and the constraint is that the likelihood of your new point has to be larger than the likelihood of the point you just discarded. I'm just going to call that disk. So that's the point you just discarded, right? So you're just saying, I'm going to take the worst point in terms of likelihood, and I'm going to sample a new point from my prior, but I will only accept it if the new point has a higher likelihood than the point I discarded. And of course, then you can see that, okay, if you just do this over and over again, you will have a fixed, a population of points of a fixed size that keeps moving upwards and upwards in likelihood, and then sort of bunch together in parameter space. So then the fifth step is just repeat from step 3. But of course, this step, this is main challenge for algorithm, let's say efficiency. Because how do you actually imagine the longer your algorithm runs, the more your prior is fixed, right? You have some prior across all your parameter space. But after running this for a while, the region where you would actually accept a new point is just a tiny part of that parameter space, but you're still sampling from the prior officially. So you can see that this will, if you do this naively, the algorithm will run slower and slower and slower and slower because you're trying to hit a smaller and smaller and smaller part of parameter space. So this is the main challenge numerically, but for now, we're just going to assume that we can deal with that. And there are packages that do deal with that, but we won't worry about it. We'll just see why this actually works. So that's the algorithm, and then the reason why you need to keep track of the discarded points is that it's the discarded points that then form this ordered set of likelihood values. Because you always discard a likelihood value that is lower than the next one you'll discard. So discarded points for ordered set of likelihood values. So that will be 0 and then L1, L2, etc. And now the index refers to the iteration in the algorithm. And so now we have an ordered set of likelihood samples, but what we needed was we need a corresponding ordered set of prior MOS values, right? Because we needed the psi L pairs. So each Li, I will now claim, and this we will go through in detail afterwards, but for each Li, we can estimate a corresponding prime mass psi I. And we'll show this later. And that corresponding, so then you get to the corresponding ordered set of prime mass values, which start at 1, and then psi 1 is less than 1, psi 2 is less than psi 1, etc. So if we can perform that estimate, then we have what we need. Then we have our ordered set of psi and L values. So then in the end, result is that we can, first of all, we can estimate the evidence. So then we can just say, okay, we now have a fairly dense set of samples along this L of psi function. So say we did m iterations of our algorithm, we can say that, okay, my approximation for this is just, okay, the likelihood value at iteration I times a weight, and then the choice of that weight is effectively just the choice of how you perform your 1D integration. So that could, for instance, it just has to be some volume along the psi axis. So then that could, for instance, be Li times 1/2 psi I minus 1, which is now the larger value, minus psi I plus 1, which is a smaller value. So that could be one way of defining those weights, Wi, according to the trapezoidal rule. But you could do whatever in that case. The point is now that you can evaluate these weights. Right? So now you have your evidence estimate. And once you have estimated your evidence, you also get your posterior samples. Because now you can say that each discarded parameter point, so the theta point that you discarded at iteration I, you now have the likelihood value for that, and you have the amount of prior probability mass that is associated with that one sample. And that's just this weight. And you have the evidence that normalizes this. So in other words, you know that the posterior sample of the discarded point at iteration I is just the likelihood at that point times the amount of prior probability that you have associated with that one sample normalized by your evidence estimate. So this is effectively assigning each discarded point theta I is share of the posterior probability. So then you have a set of samples and you have a set of weights for those samples. And then you can make histograms where the contribution to the histogram from that sample is its weight. And if you make those histograms, you'll see the posterior shape, at least if you have collected enough samples. Alternatively, so you can work directly with those weighted samples. What is often done in practice is that instead you use those weights and you sort of resample to get what's called equally weighted samples. So that's effectively what you're doing is that you're running through all your samples, and for every sample you draw a random number, and you compare it to the weight of that posterior sample. And if the random number is, less than the weight, you keep that sample, and otherwise you discard it. And by doing that, you end up with a set of parameter samples that all have weight 1, but they were retained or discarded in proportion to their posterior weight. So the reason for doing that is just that sometimes it's easier to have, here's a file of samples, and all the samples carry the same weight, and they're distributed according to the posterior, so I can just make histograms without always having to, if you do a histogram in NumPy, for instance, if you don't necessarily want to always keep, here's my list of samples and here's my list of corresponding weights, and tell NumPy histogram these samples, but keep in mind that each sample comes with a weight. You just want to say, here's a list of parameter points, histogram them. Right? So often what happens is that instead of using the weighted samples directly, you get a second list, which is the equally weighted samples, where the weight is just 1. So but there were 2 sort of open questions. One was this algorithm efficiency, and the other was how do we deal with actually estimating these psi values. Before we get into that, I will only discuss this, how to estimate this psi. The algorithm efficiency, I'll just refer to the literature effectively. But before doing that, I wanted to I want to just flip through some slides that hopefully illustrate how this goes. Okay, so here we have this 2D parameter space. The contours here are just contours of the likelihood function. And let's run this algorithm with 3 lie points, which is way too small, of course. So you start by, so this is the first step of the algorithm. You sample 3 points, the number of lie points, from according to the prior, and then you discard the one with the lowest likelihood, and you sample a new one with a higher likelihood, and then you discard the one with the lowest likelihood, sample a new one, etc., etc. You see this population of points move inwards, and you keep track of now all these yellow points are a set of discarded points that make up this ordered set of values. So
maybe it says, I didn't hear it. When do you stop? Can it stop moving anymore?
Oh, good question. Actually, I had this in my notes slightly later, but I should have said it now. What you do is that, so now we'll look at a given iteration, how much prior mass do we think is associated with that iteration? And since you have a set of lie points that is sort of within that likelihood contour, and you know the likelihood values at those lie points, you can, at any given point, you can estimate, if I take, for instance, if I take the highest likelihood value in that set of n lie points, and I times that by the total amount of prior mass that I have left, right? So how large a contribution, so that would be an L times prior mass contribution, so that would be a contribution delta set to my current set estimate. And once that contribution, So it's sort of the approximated maximum contribution that you expect remains, that might remain. Once that expected maximum contribution delta set is sufficiently small compared to your current estimate of set, then you stop.
Okay.
There's no guarantee there, and that's the tricky part. Because it might be that if you choose your number of light points m too small, it might be that, okay, sure, you have your 100 light points, but actually none of them have found this region over here that had a really large likelihood. So it might be that you're underestimating that the contribution that you could get later if you run the algorithm for longer, and then you end up stopping too early. And that's just one of the challenges, right? Because you don't know the likelihood function. So, so there's no guarantee here, but that's the stopping criterion that's typically used, that you set some threshold on sort of once this estimated delta set is sufficiently small relative to set. Say, okay, I think I'm done.
But imagining we have like a really great computer we can run forever, it wouldn't change at some point anymore.
Yeah, at some point it shouldn't change. And because all your likelihood samples would converge towards the point of maximum likelihood, and they would be associated with a vanishing part of prior mass. And that part of prior mass would go towards 0, and then it would make 0 contribution to your set estimate. So how can we estimate this prior mass? I will have to do this slightly quickly so that we make sure to actually finish this topic now. How to estimate psi I at iteration I. So from the relation d psi equals pi theta p theta, we know that sampling theta according to the prior corresponds to sampling psi from the uniform distribution 0 to 1. And just to sort of recall the sort of chain of logic between your theta sample and your psi, so just recall that if you pick a theta sample, you get you can evaluate a likelihood value. You can use that as a contour, likelihood contour threshold, what we call lambda, and that gives you integration contour for that prior mass integral. And that eventually gave you the prior mass. So that's the chain of logic that connects, in theory at least, connects your theta sample to a psi sample. The sampling constraint L of theta mu larger than L of theta discard ensures that psi mu is smaller than psi related to the discarded points. And so this means that if we always just sample our points according to the prior and we accepted every point we sampled, then we would just be sampling psi values from the uniform distribution of 0 to 1. But with this additional constraint that limits the range that we can sample from. In terms of psi, what this means is that we keep sampling from flat distributions, but the flat distribution is no longer, it starts being between 0 and 1. And after one iteration, it's slightly narrower, it's narrower, it's narrower, and narrower. It's always a flat distribution, but we decrease the range. So, say we use line points, and then at the start of iteration I, we have n theta samples that we expect statistically should now correspond to n psi samples from a uniform distribution on 0 to psi I minus 1. Right. So this was the prior mass associated with the previous iteration. So we're moving from 1 and moving downwards. And at the beginning of iteration I, we have n live points, which in terms of the prior mass is just distributed uniformly between 0 and psi I minus 1.
But the constraint lambda is kind of different from life point to another life point, right? So it could be at some iteration that we have a constraint lambda for some life point is lower than the lambda for another life point.
So the lambda is, you have a likelihood value for each life point. But to get the lambda you use as constraint, you look at all your life points and you pick the point with lowest likelihood. So the lambda you use is always the lowest likelihood among your current set of live points. When you discard that point, you sample a new one. That new one might end up just having a likelihood that's slightly better than the one you discarded, and then that new point will be the next one you discard. Or the new point might end up being the current best point, and then the next point you'll discard is whatever other part of your point in your live points. Yeah. Did that answer your question?
But when we consider another life point, then we have another set of lambda values that are iterating for, that are right.
So I mean, every live point would just correspond to one lambda value. I might not be understanding the question.
So it's the same. Yeah, that's one question. I think. Yeah. Okay.
So perhaps it's best to quickly look at this one again.
Yeah.
So every this configuration, right?
Yeah.
So I've run a couple of iterations, and so now my psi I minus 1 would be this yellow point at the bottom right.
Mm-hmm.
Yeah, and I have endpoints within that region, all at a higher likelihood. And now I want to run the next iteration, and then I look at those 3 green points and I see, okay, which one has the lowest likelihood? That's my new lambda for the next iteration.
Oh, okay.
Yeah. If that makes sense. Yeah. So the key then is that we're not trying to actually compute the prior mass accurately at every point, because that would be computationally as difficult a problem as the one we're trying to solve in the first place. but we're just trying to estimate it statistically. So prime mass psi I of the next iteration of the next, let's say, point B started is a unknown, or you might say random variable, and we can write this as psi I equals t, and I'll just call this ti times psi I minus 1, and t here is a shrinkage factor. It's a factor between 0 and 1 that just tell you how much smaller is psi I than psi. And the point is that we know the PDF for that. Where t I, which is again just this shrinkage factor minus 1, it has a particular PDF, and this is the key. It has the PDF P of t. I'll just use t because it will be the same PDF for all the TIs. So n is my set of lie points, and then we have t to the n minus 1. And what this PDF is that it's the PDF for if you draw n samples between 0 and 1 from a uniform distribution, then you let t be the largest value of those samples. What's the probability distribution for that variable? What's the probability for the largest value of n samples drawn between 0 and 1? That's this t PDF for the largest value t of n samples from a uniform distribution 0 to 1. And since this shrinkage factor is always a relative thing, right? So that's always remains a number between 0 and 1. So it always has the same PDF. So in terms of what that PDF would actually look like, it will, if you only had one sample, it would be just a flat distribution on 0 to 1. If you had two samples, it'd be just this line going up to 2. If you had 3 samples, it'd be 3 times t to the second power. So it gets more and more peaked towards high values, as you might expect. The more samples you draw between 0 and 1, the higher you expect the highest sample to be. So eventually, you end up with probability distributions that are super peaked towards high values. So this is for I, n. This is n equals 1. This is n equals 2. Since we start from the first iteration, or we start by saying, okay, we contain the entire prior mass, and we now have an expression for psi of I if you know psi of I minus 1, and we have the starting point psi 0 equals 1. So we can express psi I as just the product of the shrinkage factors, right? All the way down to T1. Sorry, that's supposed to be T1. And then at the end here, it's just psi 0, but psi 0 is just 1. So another way to express this random variable psi I is that it's just a product of I of these random variables t. And each of these random variables ti have the same PDF, which is the PDF we just looked at. you can take the logarithm. Then this, of course, just becomes the logarithm of ti minus 1, etc. And from the PDF for ti, we get, so from the PDF, we can then get the expectation value and the variance for these ti variables. Or rather the logarithm of these ti variables. So what's the expectation value for ln of t? So one of these terms in the sum, that expectation value for that logarithm is -1 over n. And the variance for the variable ln t will be 1 over n squared. And this then means that we get back to an estimate for our psi I values. So that means the get expectation and variance for ln of this prime mass. So the expectation value for ln of psi I is just the expectation value of this sum, but the expectation value of a sum is just the sum of the expectation values. So then it's just this minus n, -1 over n, -1 over n, etc., etc. This is the sum with I terms, so it's just minus I over n. And similarly, we get the variance of this quantity. And again, we're dealing with this sum, and because these ti variables, they are independent random variables. So that's the shrinkage factor in one set is completely unrelated with the shrinkage factor in another set. They're all independent samples from this P of t distribution. So then you can also say that the variance of this sum is the sum of the variances. There's no covariances popping up. So this is just minus I over n squared. So in short, we have that the logarithm of our psi I is approximately minus I over n. We turn this into a standard deviation now, is plus minus the square root of I. Don't think of I as the imaginary number, this would be confusing. It's just an integer. So we expect this for the logarithm of psi I. So that means we approximate the prior mass psi I at iteration I. We approximate that simply as psi I. It's just exponential of minus I over n. So in other words, we were able to find a sort of statistical expectation for that value, which is unrelated. You see, it only depends on the iteration number and the number of light points we started with. It's unrelated to the likely value, which isn't, I mean, if we were to actually compute the prior mass, we would have to compute that interval within that likelihood contour. But this is just a statistical expectation for how you expect the evolution of these psi I values to go. And with those psi I values at each iteration and the Li values that you get from the parameter points, then you have your ordered set of psi 1 L1, psi 2 L2, psi 3 L3. Then you have what you need. And in the end, the main uncertainty on the set estimate will come from uncertainty in psi I estimates. So this uncertainty here, this statistical uncertainty here, will be the main source of uncertainty in the set estimates. Of course, that's assuming that you have actually found that you have sampled sufficiently densely that you have covered, you found all the regions of high likelihood. If you, like we discussed, if you actually missed some region of high likelihood, then your uncertainty estimate will not encapsulate that. You will just be off, just be bad. So,
kind of transforming all the possible figures into just conical one or simple conical one, because the iteration, I mean, the size.
Yes, you effectively assume that. At least you effectively assume that through your sampling, you will always decrease the prior mass with the same expected factor, which is e to the -1 over m. Yeah. That's what you're saying. That on average will do the same shrinkage factor at every step, but you don't know that it'll do that. So this is the reason why this is how you can get those estimates. And then the challenge of sampling, which we didn't discuss, is what's solved in modern implementations of nested algorithm, nested sampling. And the two keywords there are ellipsoid sampling and clustering algorithms. So what modern implementations do is that instead of at every iteration try to sample from the entire prior, it says, I don't know exactly how to sample from this constrained region of parameter space, but what I can do is I can draw an ellipsoid which contains my current set of lie points, and that ellipsoid will roughly correspond to the region of parameter space, and I can draw samples from within that ellipsoid. So that was one of the key steps forward. And then the other key step forward was to combine that with clustering algorithms. Because if your posterior distribution is multimodal, then say half of your lie points is going to evolve towards this mode and the other half towards this point. If you now draw one giant ellipsoid, you're still going to sample a lot of the in-between region, which you will never accept. But if you cluster those and say, I'm going to draw one ellipsoid here, one ellipsoid there, you retain a lot of efficiency. So these were sort of the key ingredients in them. And this is stuff that's implemented in this multi-nest and polar chord algorithms. So I went a little bit over time, but I wanted to wrap this up. And I think with the project description, I will post some links to these packages and the Python package and stuff like that. Okay, let's stop there.